Tired of seeing this and this? Time to learn some memory management. Proper memory management is one of the most important aspects of creating applications. In C++, this is really easy. It's all based on three pillars: the notion of ownership, the determinism of object lifetime, and exception safety. First, let's talk about ownership. In the language itself, you don't really have any entity, any kind of object which defines who owns what. All you have are raw pointers, which are really bad. Let's see why. Suppose you have a function f which takes an int pointer. Now, what can you say about this pointer? Who owns it? You don't know. Does the caller own it? You don't know. Does the function own it? You don't know. Is it really a valid pointer? You also don't know. From a raw pointer you can't tell anything. Let's see what's the difference if we swap this raw pointer for something that explicitly gives us information about the ownership. Let's make a simple struct which would have pointer something very basic. Okay, so you see a very basic example of an owning structure. This structure owns its data. Of course, I know it's public and you can do whatever you want with it, but let's just ignore it for a minute. So, the structure owns the integer inside. And what happens if we pass this instead of our int pointer? Now the function knows that there is some owning object which owns the integer inside, and it knows that this object is responsible for allocating and freeing the integer. Therefore, in this function, you really don't care about freeing these resources. You know that someone who owns them will do it for you. That's defining ownership. That's how you explicitly tell who owns what. Later, we'll see how this is accomplished in the standard library. So the next pillar is determinism of object lifetime. You see, owning some resources is not enough. You have to know when the resources are allocated and when they are released. This is what is solved by our deterministic lifetime. You see, objects in C++ have really well-defined lifetime. Global static objects end their life at the end of the process. Local variables end their life when they leave the scope. Dynamically allocated objects end their life when they are deleted. It's just that simple. So, knowing that some object owns a resource, you already know when that resource will be released. This is the basis of something called resource acquisition is initialization, or RIII. I think that's how it's pronounced. I just pronounce it right. So, with this approach, you know that if an object acquires some resource, this object, at the end of its lifetime, which is well defined, should release this resource or any other resources it owns. That's how you know that if your object, for example, int, you know that when this object leaves the scope of this function, it will end its lifetime. Therefore, you know it will release the resources it owns. That's exactly how RIII works. You can find a lot of examples in the standard library. You have your streams which are closed when they are deleted. You have smart pointers which release the resources when they are deleted. Lots of examples. We'll see about them later. Okay, let's talk about the last thing, exception safety. You not only have to release your resources during normal program flow, but you also should release them when an exception is thrown. But that's really easy to handle. Rules for object lifetimes also apply when an exception is present. Let's see. Stream. When an object which owns a resource gets destroyed when an exception is present, because as you probably know, when exception is propagated upwards, the stack gets unwound and objects are destroyed, and those objects can release their resources, and using the RAI approach you'll get resource release by default. So if we have an only int in a try-catch block and we throw some exception, we will naturally get resource release in the destructor. Can we see that? No, we can't, because I didn't really call this function. Let's see. Here you go. The first object is the one which resides in the try-catch block. The second one is the argument passed to the function. So you see, even when an exception is propagated, all resources are released. That's why you should always use RAI for resource management. Okay, so with the theory out of the way, let's see how to manage resources in modern C++. Let's clear this thing. Okay. So, in the standard library you have three smart pointer classes which define the notion of ownership. You have a unique pointer, you have a shared pointer, and you have a weak pointer. First, let's talk about a unique pointer. A unique pointer is a template which owns the type you put as a template argument. In the constructor you can pass your memory, let's say 5, and now the unique pointer owns this memory and it will release it when it gets destroyed. It also has a property of being non-copyable. That means you cannot copy one unique pointer to another. You can only move a unique pointer. Let's see. Suppose we have another unique pointer. Compiler is already telling us that this is an error. You cannot share memory with unique pointers, which means you should always use unique pointers when you own a resource. If you want to own an int or whatever class you put in there, you should always use a unique pointer if you never want to share it with anyone. And of course, since a unique pointer releases its resources in the destructor, it follows the RAI approach, so it's safe to be used when exception is thrown. You also know when the resources will be deleted, so it's deterministic, it's safe, and you should use it. In the standard library you have a function called makeUnique, and you really should use that function instead of calling new to create unique pointers. Why? I will probably explain it in another lesson, but you should know to always prefer using makeUnique rather than operator new. Okay. The second type of smart pointer is a shared pointer. It's pretty similar to unique pointer, but as you probably already guessed, it allows sharing of resources. So we have a shared pointer which contains an int, and we can share it with another shared pointer. And it works. Shared pointer internally is reference counted, so the memory gets released only when the reference count gets to 0, which in practice means the memory gets released only when there are no shared pointers left pointing to that memory. As with unique pointer, you also have a make shared function, which you should prefer than writing operator new. Right. So now that you know two of the three pointer types, let's see how to use them in practice. Both shared and unique pointer have a pointer-like interface, which means you can do *pi 8, and that assigns 8 to the integer which is contained in pi. Pretty simple. By analogy, you can make it unique pointer and do exactly the same. If you need a raw pointer to the memory for some reason, maybe you have a C interface, a C library which requires raw pointers, you can also call the get method, which returns a pointer to the underlying memory, which is an int. But you should always remember, raw pointers do not convey any information about ownership, so use them with care. So we have a shared pointer, a unique pointer. We can swap one with another. You cannot make a shared pointer unique. Your shared pointers are by default shared, so they cannot become unique even if they are the only pointers which point to the memory. But you can turn a unique pointer into a shared pointer. Let's see how. By moving the ownership from the unique pointer, just like that. Now the unique pointer is empty. Its contents, its resources have been moved into the shared pointer, which can be later shared. It's also worth noting that shared pointers are thread safe, which means you can copy, move them all around in different threads and will always work. You'll get no data races. Okay, so let's talk about the third pointer type, a weak pointer. A weak pointer is a bit special. A weak pointer can only be created from an existing shared pointer. What is it for? A weak pointer is used when you need to have a shared ownership, but only for a limited time. You only need to use it, and later you really don't care if the memory is shared by anyone, the memory is there anyway. So let's see. In order to create a weak pointer, weak pointer, you should pass the shared pointer from which the weak pointer should share its resources. But weak pointer cannot be used directly as a pointer, just like a shared pointer and unique pointer. In order to use the memory contained in the weak pointer, you must first create a shared pointer from that weak pointer. So you have a shared pointer, you create a weak one, and then you create another shared pointer. It's done by calling a lock function on the weak pointer, which returns a shared pointer to the shared memory. Okay, so why exactly does it work like that? As I said, unique pointer is used to handle shared memory, but only temporarily. So, before you call lock, you really don't know if the shared memory is really there. All shared pointers could be destroyed, the memory could be released, you would never know. Only when you call lock, you create another shared pointer which really shares the memory with all other pointers. And only then you will know if the memory is still there or if that new shared pointer is really empty. You can also check if the memory is in there by calling the expired method, which returns a bool telling us if the memory is really there and you can create a shared pointer from it, or if your new shared pointer would be empty. The logic behind this is you call a lock in some small scope, you do some work with that shared pointer, and that shared pointer simply expires. The next time you want to use that memory, you must also call lock. In the meantime, the memory can be really freed. So weak pointers are really just a means to have a temporary shared ownership. Also, weak pointers can help you with dealing with circular dependencies. Suppose you have a class name widget and the class name gadget. Yeah. Now suppose widget needs a reference to gadget, a shared reference. So okay, we'll use a for declaration, and here we'll use a shared pointer to a gadget. Okay. Now let's suppose a gadget also needs a reference back to the widget. We could be tempted to use a shared pointer, but we really should use a weak pointer here. We will soon find out why. Yeah. Okay, we have our two base classes, so let's create our widget first. Shared widget. Okay, now let's create our gadget. Gadget shared gadget. Okay, so now let's create our back reference. Gadget widget. So what would happen if this was a shared pointer? Let's see. We first create a shared pointer and the reference count is 1. We then create another shared pointer to gadget. That's okay. And here lies the problem. If widget were a shared pointer, we would bump the reference count to 2. And what would happen if our first shared pointer went out of scope? The reference count would drop to 1, so the widget wouldn't be released. Therefore, the gadget wouldn't be released. Therefore, this pointer wouldn't be destroyed. So the reference count would never drop down to 0. So nothing would be destroyed. But also, since this pointer would no longer be there, you would have no way to go back to that widget and manually drop the reference count back down to 0. In other words, you would have a memory leak. But by using weak pointer, we do not bump the reference count, so when this shared pointer goes out of scope, it really goes down back to 0 and everything is released. And if we need to use this widget, we can always call lock on this pointer and everything would work. So looking at all this info, we can really summarize what pointers you should use by looking at what kind of object lifetime guarantee do we need and what kind of ownership do we need. Do we need a unique ownership or a shared ownership? Do we need a lifetime guarantee? Or do we really don't need this lifetime guarantee? You can always look at this table and choose for yourself. Should you really use raw pointers then? Yes and no, preferably no. But there are cases when raw pointers can still do their job. Let's see at our code here. We have a widget which is a shared pointer, and we can make a raw pointer. Let's just explicitly state the type. We can make a raw pointer to a widget and call get. Okay, this is correct. Why is this correct? Since this raw pointer doesn't convey any information about the ownership. It's correct because that information is contained in that shared pointer, and that shared pointer has a longer lifetime than this raw pointer. So we know that this raw pointer is valid, and we know the ownership is shared by looking at the shared pointer. But still, you really shouldn't use raw pointers, only when this is really necessary. Let's look at another function of smart pointers, custom deleters. Let's say you are working with some kind of C library and you need to allocate the memory and free with malloc and free. Okay, for some reason. Smart pointers by default use the delete operator to release their memory, to destroy the contained object. But they also support custom deleters. For example, if you make a unique pointer of an int and allocate that memory by using malloc pointer malloc size of int, you would run into a very nasty error because the unique pointer would call delete this contained object, this contained memory, and it would most likely be incompatible with malloc. Well, it depends on your internal implementation, but usually it's not compatible. So it would probably crash or in general result in an undefined behavior. So what can you do? With unique pointers you can pass your custom deleter objects as another parameter. You can specify the type of the deleter as a second template argument. In this particular case, our deleter would be the free function. So let's say that we want to use free as a deleter. Let's use decal type to let the compiler guess what type free is, so we don't have to manually write all of that. And then we should pass the actual object of the deleter type as our second argument to the constructor. In our case, this would be just a pointer to free. Voila, that's all. Our unique pointer now holds memory allocated by malloc and will use free to delete it. Let's compile this. It builds, it works, it doesn't crash. Beautiful. As I said, you also can use whole objects as deleters. So let's make our free wrapper, which will have a call operator. And this operator will take the pointer to the memory it's about to free, in our case int pointer, and let's free it. So we can now tell that our deleter will be a free wrapper, and we can pass an object of it to the constructor. By default, you don't need to pass an object, it will be created by default. Let's see. Works. Works. Beautiful. There's a slight difference if you use a shared pointer. With shared pointers, let's stick to the malloc example with with shared pointers, the deleter is not a part of the type. It's just an object passed as an argument to the constructor. So all you have to do is pass your free wrapper, and that's all that's needed. It works. You can also, in this particular case, pass a pointer to free. Works like a charm. Note that since shared pointers are shared, they will also share their deleter object. So you will always know that your memory will be freed using the appropriate deleter. Everything will be just fine. So I hope you found this informative. See you in another lesson. Please subscribe and stay tuned for more videos. You can also check out the website where you have the written versions of all lessons with somewhat more data, somewhat more code. Look it up. You can look for yourself and experiment with the code there.